US Physics Olympiad, year 2023, first round, F equal MA. In this year, it was given as usual 75 minutes for 25 problems. If you want to get more interesting problems, just subscribe for this channel. Problem number 1. A bead on a circular hoop with a radius 2 meters travels counterclockwise for 10 seconds and completes 2.25 rotations, at which point it reached the position shown. In the past 10 seconds, what were its average speed and the direction for its average velocity? Solution for problem number 1. The total distance traveled is this one, and the average speed is the distance per time, so it's 9 pi over 10 meters per second. This rules out all choices but C and E. To find the direction, we know that 10 seconds ago the bead was initially at the left side of the hoop, like on this picture. So the direction of the average velocity is this one, which is given our answer E. So that's a correct answer for problem number 1. Problem number 2. A mass on an ideal pendulum is released from rest at point 1. When it reaches point 2, which of the following shows the direction of its acceleration? Solution for problem number 2. At point 2, this is both an inward centripetal force because the mass is moving in a circle, and a tangential force because the mass is speeding up. Thus, the answer has to be a positive sum of vectors directed along A and C. So it must be B, and B is a correct answer for problem number 2. Problem number 3. A soccer ball is kicked up a hill with a flat top as shown. The ball bounces twice on the hill at the points shown, then lands on the top and begins rolling horizontally. Which of the following shows the vertical component of its velocity as a function of time? Solution for problem number 3. Since gravity provides a uniform acceleration downward, the graph of v as a function of y should be decreasing with a constant slope everywhere except at the collisions, ruling out all but choices D and E. The collisions provide the discontinuities. To decide between the two, we note that the typical vertical velocities shown in the figure get smaller as the ball nears the top, so the correct choice is E. And that was a solution for problem number 3. Problem number 4. A box of mass m is at the bottom of an inclined plane with the angle theta to the horizontal and the height h. A person drags the box very slowly up the plane by applying a force parallel to the plane. The coefficient of kinetic friction between the box and the plane is mu k. When the box reaches the top of the plane, how much work has the person done? Solution for problem number 4. When a person drags the box up the hill parallel to the plane, it must work against the force of gravity and the force of friction, which is mg sine theta plus mu k mg cosine theta. So total work done by person is force multiplied by distance. Distance equal height h over sine theta. So total work equal this expression, and the correct answer is E. That was solution for problem number 4. Problem number 5. Two blocks of mass m and a block of mass 3m are attached to a system of massless fixed pulleys and a massless string, as shown. Assume all surfaces are frictionless. What is the acceleration of each mass m? Solution for problem number 5. The system is equivalent to two disconnected outwards machines with masses m and 3m over 2 by splitting the large block down the middle. Hence the acceleration is this one, which is answer B. And this is the solution for problem number 5. Problem number 6. A ball at the end of a rope of length 0.5 meters is swung in a horizontal circle with a speed of 15 meters per second. The other end of the rope is fixed in place. What is the height difference between the ends of the rope? Solution for problem number 6. First, we have to write equations for vertical and horizontal components for forces. For vertical, we have t multiplied by sine theta equal mg. And for horizontal component, we have t multiplied by cosine theta equal centripetal force, which is mv square over L cosine theta. Now let's divide first equation by second equation. We have tangent theta equal gl over v square multiplied by cosine theta, which is 1 over 45 cosine theta. So from here we can see that theta is very small, means that tangent theta approximately equal theta and equal sine theta, which is 1 over 45. It means that height difference h equal L sine theta, or approximately 0.5 meters multiplied by 1 over 45, which is approximately 1.1 centimeters. Let's answer A, and this is solution for problem number 6. Problem number 7. Two boxes are stacked side by side on top of a large box as shown. All three boxes have mass m. The coefficient of static friction between the left box and the bottom box is mu s, and all other surfaces are frictionless. Rightward force F is applied to the bottom box. What is the minimum value of mu s so that the upper box don't slide? Solution for problem number 7. The acceleration of the entire system is F over 3m. So the total horizontal force needed to accelerate the top two blocks is 2F over 3. This must be completely supplied by the friction force mu mg on the left box. So the conclude is mu mg must be greater than 2F over 3, or mu must be greater or equal to 2F over 3 mg, which is answer D, and this is the solution for problem number 7. Problem number 8. Two stars, alpha and beta, with masses satisfying m alpha over m beta equal 10, are in circular orbits around each other. In the rest frame of this system, find the ratio of the speed v alpha over v beta. Solution for problem number 8. Because the total momentum is 0, we have m alpha v alpha equal m beta v beta. And from here The answer is V alpha over V beta equal 1 over 10, which is answer B, and that was solution for problem number 8. Problem number 9. A helium balloon is released from the floor in a room at rest, then slowly rises and comes to rest, touching the ceiling. During this process, the gravitational potential energy of the balloon has increased. Since energy is conserved, the energy of something else must have decreased during this process. Which of the following is the main contribution to this decrease? Solution for problem number 9. The main contribution is choice E in terms of energy. Objects that are lighter than air float upward because the air can move downward to where the object originally was, thereby reducing its gravitational potential energy by more than the gravitational potential energy of the object went up. So correct answer is E, and that was a solution for problem number 9. Problem number 10. An archer takes aim at a target that is 100 meters away. Assuming she holds the ball at the same height at the center of the target and shoots an arrow with the velocity 100 meters per second, at what angle above the horizontal should she aim the ball so that the arrow hits the center of the target? Solution for problem number 10. Since the initial and the final heights are the same, we can apply the range equation. Distance equal v square sine 2 theta over g. From here we can find that sine 2 theta equal rg over v square, or 1 over 10, which give us this answer, which is answer D, and that was a solution for problem number 10. Problem number 11. A projectile is thrown from a horizontal surface and reached a maximum height h, and also lands a distance h from the launch point. Neglecting a resistance, what is the maximum height for a projectile thrown directly upward with the same initial speed? Solution for problem number 11. For a maximum height, we know that h equal vy square over 2g, and from the range we know that h equal vx multiplied by total time, but the time equal 2vy over g, and combining this we have vx equal h over t, or gh over 2vy, or just 1/4 of vy. So from the first equation we have vy square equal 2gh, and total speed v square equal vx square plus vy square, which is 17 over 16 vy square, which is 17 over 8 gh. And last, for the second case, we have height equal v square over 2g, or 17 over 16h, which is answer A, and this was a solution for problem 11. Problem number 12. A block of mass m is initially held in place by two massless strings, as shown. The tension in the diagonal string is T1. Next, the horizontal string is cut, and immediately afterward, the tension in the diagonal string is T2. Which of the following is true? Solution for problem number 12. Let the angle from the vertical be theta. Before the string is cut, balancing vertical forces give us T1 cosine theta equal mg. And from here we have T1 equal mg over cosine theta, which is greater than mg. Right after the string is cut, balancing force along the direction of the string give us net force 0. It means that T2 must be equal mg cosine theta, which is less than mg. Both of this equation give us a relation B, which is a correct answer. So that was a solution for problem number 12. Problem number 13. A uniform box with mass m is at rest on the horizontal surface and the coefficient of static friction between them is mu s. A force directed at an angle of 85 degrees above the horizontal is applied to the center of the box with a linearly increasing magnitude f equal beta t. The box will eventually slide or lift off the ground. Which of the following is correct? Solution for problem number 13. The box will slide first, no matter what the other parameters are. The box will only lift off the ground once the normal force goes to 0, which occurs when the vertical component of the applied force exceeds the weight of the box. Right before that moment, the normal force will be very small, so the maximal possible friction force is also very small, and cannot balance the horizontal component of the applied force. So the correct answer is D, and that was a solution for problem number 13. Problem number 14. The object shown below is made of 3 rigidly connected identical rods with a uniform density. When it stands upright on a horizontal table, what fraction of its weight rests on the left leg? 14. Let each rod have weight W over 3. Let the normal force on the left leg be N, and let the distance between the legs be L. If we balance torques about bottom of the right leg, then the only contributions are from the weights of the rods and the normal force N, which is giving us equation. Torque from normal force N equal NL, which is equal to W over 3 multiplied by 3 distances from center of mass of each of the 3 rods, which is L over 4, L over 4, and 3L over 4, which is giving us 5 over 12 WL. And from here we have N normal force on the left leg is 5 over 12 W, which is answer E, and that was solution for problem number 14. Problem number 15. The following plot shows the speed Vr at which stars orbit about the center of a galaxy as a function of their distance r from the center. Assuming the galaxy has a spherically symmetric mass distribution, which plot best shows the mass of the galaxy mr enclosed within radius r? Solution for problem 15. The graph shows that rotational speed becomes roughly constant once a certain distance from the center galaxy, but the rotational speed of mass m is governed by equation, this one. Then we must have a linear dependency mass of distance r to keep v constant, which correspond to choice B. Choice D does not match this behavior because it is more like parabolic for big R. However, at the level of resolution given in the figures, it is somewhat difficult to see that its curve indeed remains parabolic at large R, rather than approaching a linear dependency. Furthermore, it is below linear as at small r, which is consistent with the small r behavior for V. Thus, we also accept D as correct. So B and D are correct answers, and that was a solution for problem number 15. Problem number 16. A bead attached to a string of length L equal 10 meters is released from a very small angle θ0 to the vertical. A wall is placed in the path of the bead such that the bead collides elastically with the wall when the string is at an angle θ0/2 to the vertical as shown. What is the interval between the bead's collision with the wall? Solution for problem number 16. The angular frequency for this construction will be omega equal square root from g/L, which is 1 Hertz. For that frequency, we have a period equal 2 pi over omega or 2 pi seconds. Equation for this motion is omega equal omega 0 multiplied by cosine omega t. The moments when the bead reach the wall in position when cosine equal negative 1/2 are t1 and t2. So we need to exclude from this oscillation time from t1 to t2, and total time between collisions will be period minus t2 minus t1, which is 4 pi over 3. That's answer C, and that was solution for problem number 16. Problem number 17. 3 physical pendulums are built as shown. The first is a typical pendulum with a massless rope, and the second and third are made of uniform rods. What is the correct ranking of the moments of inertia I1, I2 and I3 about the pivot points? Solution for problem number 17. This is a straightforward application of the standard moment of inertia formulas. So for the first pendulum we have I1 equal ml square. For the second pendulum we have 1/3 ml square, and for the third pendulum we have 4/3 ml square. So from here we have this relation, and the correct answer is E, which is solution for problem number 17. Problem 18. Alice, Bob and Carol are each given identical airtight bags containing identical rocks and a large tube of water with a scale sitting on the bottom. Each of them measures the weight of their bag and the rock by putting the bag on the scale, using 3 slightly different procedures. Alice closes the bag carefully so that there is no air inside. Bob fills the rest of the bag with water before closing it. Carol closes the bag loosely so that it contains some air. What is the correct ranking of their measured weights, WA, WB and WC? Solution for problem number 18. The scale's measurement is the weight of the object not supported by the buoyant force. In other words, the scale measures mg minus rho vg, where m is the mass of the bag with rocks, rho is the density of water, and v is the volume of replaced water. For Alice we have this measurement. If Bob adds volume delta V of water, he adds mass rho delta V as well. And practically we have the same measurement for him. Carol adds a volume of delta V while adding a negligible mass from the air. So we have the same but weight of replaced water by additional volume of air. Therefore, the answer is E, and that was a solution for problem number 18. Problem number 19. A student sets up a simple pendulum, measures its length to be L equal 0.5 no 0.50 plus minus 0.01 meters, and observes a period of oscillation of t equal 1.4 plus minus 0.1 seconds. Using this data, the students compute g equal 10.1 meters per second square. What is the uncertainty of this measurement? Solution for problem number 19. From formula for mathematical pendulum we have g equal this expression, and we can use the standard rules for propagation of relative uncertainties. The relative uncertainty of a product or ratio of two quantities adds in quadrature, and the relative uncertainty of a squared quantity is doubled. From this we can use this formula. Delta G over G equal this expression. Thus we have delta G equal 1.4 meters per second square, and that's answer C, and that was a solution for problem number 19. Problem number 20. A mass attached to the end of a string oscillates like a pendulum with a small amplitude. The mass has a horizontal velocity Vx and a vertical velocity Vy as functions of time. Which of the following could be a graph of the curve Vx and Vy over a complete oscillation? Solution for problem number 20. The answer is choice C, because it could be shown by plotting several points. For example, one simple way to rule out the other answers is to note that on a pendulum, Vy hits 0 4 times per cycle. When it reached the maximum displacement, vertical speed is 0, and when it hits the equilibrium position, that would be twice. Again, vertical speed is 0. So that's the answer C for question number 20. And that was solution for problem number 20. Problem number 21. Smooth ring of radius r and mass m lies on a frictionless surface. A point mass also of mass m is placed just inside the ring and given a speed v tangent to the inner surface of the ring. How long does it take for the point mass to return to its initial position relative to the ring? Solution for problem number 21. The masses are undergoing small elastic collisions. During an elastic collision, the magnitude of the relative velocities between the masses are conserved. So the tangential velocity of the mass m relative to the ring is always v. Thus the time is 2 pi r over v, which is answer C, and that was a solution for problem number 21. Problem number 22. Two springs with different spring constants are connected in three ways as shown. In the second case, the springs are connected to opposite ends of a string, which runs under massless frictionless pulley. In each case, the two springs act like a single spring with an effective spring constant Ka, Kb, or Kc. Which of the following is correct? Solution for problem number 22. Let the springs have spring constants K1 and K2. In the first case, the forces of the springs simply add. So we have F equal F1 plus F2, which is equal to K1 delta L plus K2 delta L, which is equal to K1 plus K2 delta L, or effective spring constant Ka equal K1 plus K2. In the third case, we have same force applied to both strings, so we have force F equal K1 delta L1, or equal to K2 delta L2, and then from here we can find what is delta L1 and delta L2. We have to summarize them to find what is total dl, and after that dl equal to F multiplied by 1 over K1 plus 1 over K2. It means that Kc equal K1 K2 over K1 plus K2. The second case is not more common, but it's similar to the third case, because here we have the same force acting on each spring, but now they are connected more like in parallel. So it means that if we apply to each string force F, we have resulting forces 2F, and also enlargement dl1 and dl2 now distributed twice. So it means that we have to take dl over 2 compared to the third case. So it means that we have force twice greater than in third case, and enlargement twice less than in third case. So totally we have Kb equal 4 times Kc, or 4 K1 K2 over K1 plus K2. So it means that we have Kb greater than Kc, but Ka greater than Kb, because mean arithmetic greater than mean geometric. Correct answer is A. That was solution for problem number 22. Problem number 23. An astronomer on Earth, which is a distance LE from the Sun, observes a star and galaxy. The star is a distance LS much greater than LE away, and the galaxy is much further away than the star. Throughout the year, the angular distance between the star and the galaxy appears to vary, reaching a minimum of 2 astroseconds on January 1st and a maximum of 2.5 astroseconds on July 1st. 1 degree is equal to 3,600 astroseconds. Assume the Sun, star and galaxy do not move relative to each other, and that the Earth's orbit lies within their plane. What is the ratio Ls over Le? Solution for problem number 23. The change in apparent position of the star is due to parallax. Using the small angle approximation, we have delta theta equal 2Le over Ls, where delta theta equal a difference between 2.5 and 2 astroseconds, which is 0.5 astroseconds, which is 1 degree over 7,200, or about 2.4 multiplied by 10 power negative 6 radians. Solving this ratio, we have Ls over Le equal approximately 8 multiplied by 10 power 5, which is answer D, and that was solution for problem number 23. Problem number 24. A very heavy plate continuously moves up and down with a small speed v, switching directions after each time t. At a random time, a ball is dropped from rest far above the plate, then bounces elastically off of it. How does the ball's speed change during this collision? Solution for problem number 24. Solution for problem number 24. Suppose that our plate moving from position 1 to position 2. It has the same probability to move from position 1 to position 2 and from position 2 to position 1. So let's see what happened when the ball reaches position 1. In that moment, if a plate has position somewhere between 1 and 3, this ball will reach this plate during time when it's going down. And when plate is going from position 3 to position 2, still down, this ball has no time to reach it. So it means that during time when plate going from position 3 to position 2 and from position 2 to position 1, still our ball will collide with the plate when the plate is going up. So it means that probability to collide with this plate when it's going up greater than probability when plate going from position 1 to position 3 down. Means that correct answer is D. The ball is more likely to speed up than it slow down. This is the sample model for how a gas heats up in a container with hot walls, or more exotically the Fermi acceleration mechanism for cosmic rays. That was a solution for problem number 24. Problem number 25. A skier slides from rest along a frictionless slope with the incline angle theta equal 30 degrees for 150 meters. Then smoothly transitions into a horizontal jumping ramp of height hr equal 5 meters. Neglecting air resistance after the skier leaves the ramp, about how far will they travel horizontally before landing? Solution for problem number 25. Upon leaving the ramp, the skier has a speed v equal square root from gd. From there, the skier travels a horizontal distance x equal vt, where t is the time of flight. To find this time, it's better to use a coordinate system where x direction is along this slope and y direction is perpendicular to this slope. So now we have in this coordinate system, initial vertical speed is v multiplied by sine theta, or square root from gd over 2. Also we have downward acceleration equal to g cosine theta, which is g square root from 3 over 2. And the initial height is hr cosine theta, which is hr multiplied by square root from 3 over 2. Now we have to solve quadratic equation as usual. So we have final height equals 0, and that's equal initial height plus initial vertical speed multiplied by time minus downward acceleration multiplied by t squared over 2. And the time will be positive root of this quadratic equation, which is this one. And the last step is to find what is total horizontal distance. That will be v multiplied by t, which is about 181 meters. That's answer C, and that was solution for problem number 25.